Welcome to Math 106, Chapter 3.3, where we're talking about implicit differentiation and related rates. Now, because this is going to be a bigger section, we are going to be splitting this section into two parts. Part one, where we will focus on the implicit differentiation, and then our next video will be on related rates. So in this section, there are two different applications of the chain rule. We will need to differentiate one or more composite functions where the inside functions are not known explicitly. Now, implicit differentiation, in some applications, the variables are related by an equation. Rather than a function. We can still determine the rate of change, your derivative, of one variable with respect to the other by a technique of implicit differentiation. So what you're going to be seeing is that we're going to have more than one variable, and now we need to derive both variables at the same time, where one variable is going to be the primary variable, and your second variable is going to be derived, but in terms of the first. So we denote that the slope of a curve at your point here, 1 and root 3. So looking at 1 and root 3 here. And if we wanted to know the slope of your curve, right, because we have an x and a y coordinate, we would want to derive dy over dx, given that your x is equal to 1 and your y is equal to your y coordinate, the square root of 3. So again, dy dx is the slope. And what we end up doing is that in the end, we will substitute in these two variables. So in general, the slope at the point AB, so at any point AB here along the line, kind of keep in mind AB is now a coordinate. We're so used to just saying, okay, here's this function, which is our circle of function. No, it doesn't pass your vertical line test. So instead, we're going to be seeing some sort of an equation here, such as this circular one, x squared plus y squared is equal to 4, where you can tell we have two variables and we need to take the time to derive both. And instead of just saying, okay, well, let's find your derivative when f of x is 3, right? When x is equal to 3. At this point in time, we are now given some sort of coordinate that we need to plug back into your derivative to find your slope at that particular point, right? Because a point A, B has an x value and a y value. So if we were to do it again, in some general case, we would end up with dy dx, given that we're trying to figure out the slope when x is A and when y is B, some sort of point along this line or along this circle. Now, if we were to look closely at the point AB, the curve looks like a graph of a function. This is why we can actually still go ahead and take your derivative. Because if we hone in and just say, hey, maybe this is the only picture I gave you, right? This curve, it looks somewhat like a function. We can still determine the slope of that particular area. So we can say that this function is defined implicitly by the equation. We obtain the formula for dy dx by differentiating both sides of the equation with respect to x. X is your independent variable, so that one is like the primary variable. And when you treat y, it's going to be treated as a function of x in a relation with x. It is your dependent variable. So that was a lot of words to explain that. Okay, when it comes to some sort of equation with two variables, and you can notice there are two sides, x squared plus y squared is on one side, and then 4 is on the other. So when we create steps, and it says use implicit differentiation to compute dy dx. And again, there's two variables here, so we need to derive slowly at first. Now, my hope is that by the end of this video, you will not feel like you need to do these step by step, and instead just look at it once and derive all together. But first, let's say we derive from what we know, right? Just with one variable. So step one, derive in terms of x first. So if we have x squared plus y squared is equal to 4, I'd like you to just ignore your y for now. Could you go ahead and derive anything that's not a y, right? Given what we know about derivatives. So we should get 2x, ignore your y. Now, how does 4 derive? Well, 4 is your constant. Therefore, it's going to be equal to 0. So now step 2, let's derive the y term and add, and this is the most important part, add dy dx. This is the new portion of it. Now, if you forget to add dy dx, you are not, you haven't derived properly. So it's more important than you think. So if we start out with 2x plus y squared is equal to 0 from the above, let's go ahead and derive your y term. Well, that would be 2y. I finished my deriving of my y, and I tack on dy dx is now equal to 0. So I've derived both of my variables. Now, when it says to compute dy dx, that is in a way saying, can you solve now for dy dx? So step 3, and step 2 was pretty much now derive y. So step 3 is solve for dy dx. Get dy dx alone. First thing that we would perhaps want to do, after I, of course, write it down, is subtract over your 2x and then we can divide by our 2y and simplify. Dy over dx. Notice that we have 2 2's that can cancel. So we get negative x over y. Now let's have you try another one. Let's have you try, let's see. Number 2, how about that? Y to the 4th minus x to the 4th is equal to y squared minus x squared. So step 1, derive x. Y to the 4th minus 4x to the 3rd is equal to y squared minus 2x. Step 2, derive y and add dy dx. Each time you derive your y variable. So we have 4y to the 3rd, finish deriving my y, add dy dx, minus 4x cubed is equal to 2y, finish deriving my y, dy dx, minus 2x. Last step, solve for dy dx. Treat it as a variable. Well, what would you have done in the past if you've had this sort of variable? right? Well, there's two of them. They're on opposite sides, so get them to one side. So that just means bringing your 2y dy dx d over. These both have dy dx, dy dx. Perhaps you add 4x cubed to the other side. Now start to solve, right? Now start to simplify. What can we do on this side if we have two of the same term? Well, we can factor out your dy dx, leaving behind 4y cubed minus 2y. And yes, if you wanted to, you can factor out your 2 and your y. I would say wait till the end to do that. You could do it to the other side though. Notice that we have 2 and an x in common. And lastly, let's go ahead and divide by 4y cubed minus 2y. So dy dx is equal to 2x squared minus 1. And at this point, if you wanted to factor out your 2 and your y from the bottom, we certainly can. Simplify x, 2x squared minus 1, y, 2y squared minus 1. This would be your dy dx. Let's try one more. Let's try x y cubed is equal to 2. See if you can pause the video and try these out. Well, we do have the product rule here, which keep in mind the product rule, how it goes. Just says f prime of x times g of x plus f of x times g prime of x. So in our case, what is one of your f of x's? Well, that would just be x. Let's go ahead and derive x. G of x can be your other variable, y. Try that y over. There we go. Go ahead and derive y. 3y squared. And again, you finished deriving y. We need to add dy dx. Now let's go ahead and put that back together. So we have your product rule, which says your first derivative of x, that would just be 1, times y cubed plus f of x times 3y squared dy dx. That is from this portion right here. Now let's go ahead and derive the other side. So deriving the other side, we should get just a 0. Okay. So now let's go ahead and solve for dy dx. Let's bring over your y to the other side. Let's go ahead and divide by 3xy squared to the other side. So simplify. We should get negative y over 3x. And again, it's negative y because we have 3 y's up top and 2 on the bottom. So it's top heavy with y's. And so we should have the very end here. let's see what else we have. So now it says with B, so kind of, I believe, a continuation from our previous one. It says find the slope of the graph at the point 1 root 3 and 1 negative root 3. So for us, we're just kind of extending on from what we have. We now have your derivative right here. dy dx is equal to negative xy. We'll throw that over here. dy, oops, dy dx is equal to negative xy. And we want to know the slope at the particular point when x is 1 and when y is the square root of 3. And again, we're going to do it one more time. Copy, paste, with x being 1 and y being negative root 3. Now see what we can come up with. So here we have negative 1 over the square root of 3. Now this is where we are going to rationalize. Rationalizing just means that, hey, sometimes we need to simplify your denominator or simplify your numerator. Perhaps there is an issue going on, in which case, if we have a square root, typically we are going to get that out of the location. So we do this typically when your square root is in the denominator. However, it does not exclude it from the numerator. So in doing so, we get to multiply your denominator by itself. We always rationalize the radical. So you multiply it by itself always. And what's going to happen is that when we bring these two together, this is really the square root of 3 squared. Or you could say, well, they are both underneath a square root, so they get multiplied together. So now we're looking at the square root of 9, which is 3. Or the square root of 3 squared. They'll undo that process and just make a 3. So rationalizing, once you multiply your denominator by itself, it comes up with itself. So you get a 3 on the bottom. Now up top, we just need to simplify. So we get negative square root of 3. This is the slope, negative root 3 over 3 at the particular point of 1 root 3. Let's see if you can try it again on the other one. So we have negative x over negative square root of 3. Your negatives cancel. And let's go ahead and rationalize, multiplying the bottom and the top by your radical. We should get x root 3. Oops, so sorry, not x root 3. I forgot to put my 1 right here. So we should get the square root of 3 up top over 3 on the bottom. Again, this is the slope at the point 1 root 3. Now there's a theorem for this. It says d over dx is equal to y to the r, which you're just going to perform. It's just saying, can you derive y in terms of x when y has a power? When y has a power, we're going to bring that r down as we normally would. R comes down, y stays the same. And then with your power rule, we subtract the 1. The only difference with deriving y is that we now need to tack on dy dx. This is just saying, can you derive your y term? Again, this is the exact same as the power rule. Same as the power rule. Just add dy dx. So let's have you guys try the next few examples. So hopefully you are on pausing the video. We have dy dx that we want to figure out, and we have your following equation. And we did some warm up this kind of similar problem on our previous page, right? Where we said, hey, this is really the product rule. Your product rule just says that we are going to derive x times g plus f of x times the derivative of g of x. So let's say f of x is equal to x squared. Let's go ahead and derive x squared. G of x, we can say, is y to the 6th. Now let's go ahead and derive y to the 6th. 6y to the 5th, we completed your derivative. Now we need to add dy dx. Let's go ahead and put it all back together. We have 2x y to the 6th plus x squared times 6y to the 5th dy dx. So that is the derivative on one side. Now let's take the derivative of the other side. Derivative of just your constant is 0. Now let's go ahead and start to solve for dy dx. So bringing things across the equal sign. On one side, we should have this value. The other, we are subtracting 2xy to the 6th. Lastly, let's go ahead and separate your coefficient from dy dx. So dy dx, and simplify that other side. Well, 2 and 6, they both leave behind. We have a 3 on the bottom, a negative. Let's see, we have 1x and 2 down below. So we have an x here. And we have 6 y's up top and 5 on the bottom. So we're going to leave it behind 1. And there you go. So example 3, and if you didn't pause initially, definitely pause here to try it out. So here we have the power rule twice. So I'm going to write that down twice over here. Copy. Paste. I'm going to paste it one more time. So notice that your first term we have x squared y. In your third term or second term we have xy cubed. All we have to do is just make a small adjustment to these. Actually, that one will just be 1. Your second term, again, small adjustment here. Let's see, y cubed. And of course, I'm fiddling with it, so I'm just going to spend a moment checking over my work. So let's see, x squared, we get 2x. Y, we get 1 dy dx. X here becomes 1. Y cubed, which I forgot my y cubed here, becomes 3y squared dy dx. So those are my first two terms together. So when we go to bring it back together, I should have 2xy plus, let's see, x squared times 1 dy dx. So this is all from my first term here. My second term is this second product rule right here. So we have 1 times 1 times y cubed plus x times 3y squared dy dx, and that is coming from this here. Now we can go ahead and derive my third term, -3, and our other side, that's a 0. So now let's go ahead and start to bring some terms together, start to simplify. So I'm going to keep dy dx terms on one side, and then everything else should come over to the other side. So on the other side of my equal sign, I should get a -2xy. So this term I'm going to subtract to the other side. Same thing here. I'm going to subtract my my y cubed to the other side. And I'm going to add my 3 to the other side as well. So bring all of that over. So on the opposite side, I should get x squared dy dx plus 3xy squared dy dx. So anything that had a dy dx term, we're going to keep to one side. Let's go ahead and factor out what they have in common, which is that dy dx to start. We can factor out more later. There we go. Let's go ahead and divide. So we have dy dx and is equal to negative. And this is where we could factor some things out. I'm not in love with having my negative leading coefficient. I also might want to rearrange it so that my I'm going in descended order by power. So I'm going to take out my negative, go in descended order. These two, because they're different exponents or different variables, I can just add their exponents together. So this term has a degree of 2 minus 3. Down below, I'm going to factor out my x. And there you have it. So this is probably my final product. Now, before we end this video, I just want to go over kind of just finding the terms, but just defined by your textbook. So it says find dy dx by implicit differentiation. So differentiating each term of the equation with respect to x. Treat y as a function of x. Move all terms involving dy dx to the left side of the equation. It doesn't really matter which side, but usually we have our equal sign on the left. Factor out to your dy dx on the left-hand side of the equation. So that's exactly what we did. And then divide both sides of that equation by whatever it's factored is multiplied. So think about our coefficient. Typically, we divide out. That is all that we are saying. Now, equations that use implicit differentiations are a lot of these economic modeling problems. So move on to chapter 3.3, part 2, where we talk all about related